See, we're good.
Does this light bother you guys? Like on the camera? Because I don't know, sometimes it seems hard to read to me. But... Okay. Let's get back into it. Some problems to solve. Oh, I also said I would solve the ones that we already solved using the tabular method to show you how things will work. I believe one of the first examples we did was this guy, x e to the x dx. Right? And we did that with the integration by parts formula. And I just want to show you what it would look like to use tabular integration on this. You can. So you notice that here, this is guys like your u, that is your dv. That's how you choose based on Liate. So you can set up a table right below that. Differentiate the x, you get 1. Differentiate that again, you would get 0. So you can stop right away. Integrate, integrate, and then you do that diagonal multiplication. So that's a plus, that's a minus, and come across here. The integral of that is going to be just a constant, and so you really just have x e to the x minus e to the x, and then integral of 0 plus c. So that was the integral of 0. So that was very anticlimactic. I mean, it's a one-step integration by parts process. So you can actually use the formula once, or you can use the tabular method. So that's when we went to 0. We did another example, I believe, where it didn't go to 0. ln x dx. In this situation, according to Liate, this should be your u, and that should be your dv. So probably what I would do here is actually write it in the other way. But now you notice that once you start differentiating, this guy's never going to go to 0. It's going to go to 1 over x, then minus 1 over x squared, and then you're going to have something 1 over x cubed, etc. So how you kind of deal with that, because it'll never hit 0, you differentiate once, you integrate once, and then you notice that, hey, if I multiply these two, that's going to be pretty easy. So you just stop there. So you have a plus times this, minus the integral of that, and so you would get x cubed over 3 times the ln x minus the integral of 1 over x times x cubed over 3 dx. And that's exactly what you would have gotten had you used the formula. And so this goes into that, so you have the minus x cubed over 9 plus we did that one that you got the thing back, so e to the x sine x, I believe we did. So according to Liate, the sign should have been our u, so I actually write that in front. So that's my u, that's my dv. So I can start setting up the table. I can differentiate this, I would get cosine of x. If I integrate that, I would get e to the x. Differentiate this, I would get minus sine x. Integrate that, I would get e to the x. And then I notice that, hey, this guy here is exactly the same as that guy there, of course with a minus sign. But in either case, I'm going to stop. So it's going to be this times this plus this times this minus that times that plus, but this one gets an integral sign on it once you go back that way. And so we end up having this equals e to the x sine x minus e to the x cosine x plus the integral of minus e to the x sine x dx. And at this point you'll see that, hey, that guy is on both sides, so I can move this over here. Of course there's going to be a plus c. And then we can finally end up with that. So just so you have something to compare to, you can decide which way you prefer doing and just do it that way all the time. But either one will work. Where this method really shines, like I said, it's when you realize you have to do a bunch of integration by parts, and that can get pretty annoying and pretty hairy. Any questions on this? So yeah, then I left you guys with some examples. I didn't actually label them on my paper, so I don't even remember what I asked you technically. I think this was one of them. E to the radical x. X cubed, e to the x squared. Did you do tan inverse of x?
Yeah.
We did that.
No.
Oh, okay, that was one of them. Okay, good. D. I said we were going to do that x squared ln x thing, so I think that's the one we did. But using the tabular method, which now you've just seen, this is done. We also had x squared e to the x cubed. We also had radical x cosine of radical x dx. We also had x cubed sine of x squared dx. And once we get through those, we'll be finished with this section of integration by parts. Like I said, I taught Calc 1 in the spring, I taught it again in the summer, and teaching it again now, like, sometimes you can't keep anything straight. Anyway, just today I was talking to the class and I kind of realized it kind of felt bad how this whole Calc 2 thing started. Felt like I needed to apologize to you guys or something, because I was there and I was talking to the kids. You know when you think back to a simpler time, when the world was full of wonders, and I was talking to them, I was like, do you guys know what calculus is? Oh, it's amazing, it's so awesome, and there's this thing called the rate problem, the error problem, and we can actually solve this even though it seems like impossibly crazy to solve, and they're like, really? And I was talking to them that, yeah, there was Newton and there was Leibniz and this was going on and that was going on, and hey, there's this thing called the limit, and you hype them up and you kind of, and now it's like, I feel like in Calc 2 I was like, y'all know what the deal is. Integration. Let's just jump into a technique. Let's go. Come on. Yeah. But yeah, that's how it starts. Okay, let's actually do it. Let's just keep going. What do we do here? What do you do? What do you try? Anybody go? Yeah.
Substitution.
So substitution. Okay.
U equal to root x.
You said u equals what?
Or u equals root x.
Okay.
And then I derived that to find du. So du dx is equal to 1 over 2 root x dx. And then, so dx is equal to 2 root x du. And so now you have 2 root x e to the u. And so you can take out the 2. You can factor out the 2, and then you have a u.
Okay, so 2 root x e to the u.
And then you can factor out the 2, change the root x to a u, and then use the tabular.
Right, so use the fact here. Of course, we're doing du, so we can't have that x here. And so what you did is just, you already know that the radical x is a u. So we substituted that for u while factoring out the 2. Right, and then that one is, how do you do that?
You just tabular method. So
Yeah, or integration by parts.
Yeah.
So one comment here is, of course, the u here is not the same as the u in integration by parts. So sometimes if you realize, hey, an integration by parts is coming up, one thing you can do is actually do a different substitution. Like, if you're doing tabular, there is no problem. There is no conflict here. So no conflict with tabular. But the by parts formula has a u in it, so you have to be as u. So there is some cause for confusion. So the solution to this conflict, if you know parts is coming up, use another variable. That's all it is to it. So you could have done exactly the same thing if you're partial to using the formula, but you can set, say, t equals radical x. You can do all the same things here. So your dx would be 2 radical x t, or in other words, it's going to be 2t dt. And so we would have the integral of 2t e to the t dt. And now when you set u equals t, it doesn't look like you're saying u equals u, and the u's are actually different. And the dv equals e to the t dt, right, etc. Or you can just like do tabular if you wanted. That's 1, that's 0, that's e to the u, that's e to the u. It's going to be a plus this, minus this, plus c. Either way, we end up with, well, the u is the radical x. So we're going to end up with our integral is radical x e to the radical x.
You have to distribute the two. Yeah.
I forgot the 2. Minus e to the radical x plus c. 2. Okay, so you can actually integrate that, which might be surprising, but you can. Like e to the x squared, impossible. E to the radical x, which looks really weird. No, possible. Totally doable. Lead with a substitution, finish off with an integration by parts. E. What do we do here?
Substitution.
Okay, what?
U equals x squared. So then du is equals 2x dx, and dx equals du over 2x.
So you can plug that in.
So the x will
This x is going to cancel with that one.
And you can substitute u again.
And we are going to get u for that x squared, so we're going to have 1/2 u e to the u du. You saw that again, that's u e to the u minus e to the u plus c, and then you back substitute. Right, when you plug in the variable, it's called back substitution. So this will end up being x squared e to the x squared minus e to the x squared plus c. The plus c can be inside or outside of parentheses, it's not going to matter. So that's that. Very similar. C, integral of tangent inverse.
Integration by parts.
Okay, what are the parts?
U is tan inverse and dv is dx. And 1 dx.
Mm-hmm. So your du is,
1 over 1 plus x squared dx.
and your v is x. And so you would end up with the integral equals u times v minus the integral of v du. At this point you do a substitution, u equals 1 plus x squared, a half ln of 1 plus x squared, which technically you don't need the absolute values, but let's just put it to be safe. That's the substitution. U equals 1 plus x squared. And E, seems like it's going to be similar to that. Or is it? This is x squared. So, what do we do here?
U substitution.
Just a substitution. And we don't need anything else, so that was just that. So hopefully you didn't try it by parts there, you didn't need it. Integral of radical x cosine of radical x dx. Okay, what do we do here?
Substitution. U equals root x.
So now what would we have? We would have the radical x is a u, radical x here is a u, times the dx is a 2u. And so what we end up with is 2 times u squared cosine u du.
And then to do tabular
And
integration
then,
by
or
parts.
do tabular, or integration by parts. Differentiate that, and integrate this, positive sine, integrate that, negative cosine, integrate that, negative sine, and so it's going to be 2 times plus this minus this, which turns it into a plus, plus that, plus, minus, plus, which leaves it as a minus 2 sine u, and then integral of this product, which is going to be your plus c. So we're going to have 2 times, the u was radical x, so that just becomes x sine radical x plus 2 radical x cosine radical x minus 2 sine radical x plus c. Good. G. trying to thinking of how we can spice things up. Maybe we'll have an integration gauntlet at the end of chapter 7.
Integration.
Prize, party. Okay, what do we do here?
Substitution, u
Yeah.
equals x squared.
Right. That's a tough thing to get away with because we know that sine of x squared has no integral, so I probably want to write that x squared as a u. So dx equals du over 2x. So you go and you plug that in. This cancel that. Get a u squared. So this leaves you with x squared, which is u. 1/2 comes out. Another table. This is going to be 1/2 times plus this, which ends up being a minus u cosine u, minus that, which ends up being a positive sine u, plus c, 1/2 sine x squared minus x squared cosine x squared. Is that what you guys got? Alright, that's it. That's integration by parts. Just another technique, another tool in the tool belt. We're going to learn about yet another tool in the tool belt. Trig substitution is what it's called. But before that, let's actually talk about trig integrals in general. So that's the next section. So for those of you following along, we're now in 7.2. So trig integrals, that's how the section starts. And it ends with something called trig substitution, short for trigonometric. So the main idea here in this chapter is we're going to use trig identities to help us integrate trig functions or trig-like polynomial functions, and I'm going to talk about what that I mean by that when we get to it. Okay, so that's the main idea. So you're going to have to remember your trig rules, your trig identities, all that good stuff. Some integrals that will come in handy. Knowing how to integrate tangent and secant is often going to come in handy. We already know how to do sine and cosine. As for cosecant and, let me just write that down. We'll omit cosecant x and cotangent x since they operate by rules similar to the tangent and secant rules. Right? So I'm not going to do any examples with these guys, and I'm almost never going to test you using those guys. Because once you know how to do everything with tangent and secant, you'll know how to do it with this. So why force you to memorize yet another formula? So sine and cosine are their own little ball game. Secant and tangent are their own little ball game. But once you know how to play the game of tangent and secant, you'll automatically know how to play the game of these two. So we're going to focus on sines, cosines, secants, and tangents. Let the games begin. So let's first start with tangent. That is actually something that you should know how, if you don't have it memorized, you should know how to get to that, actually. So, what is the integral of tangent? Or if you don't remember, how would you figure it out? Yeah?
You can do integration by parts.
What would your parts be?
U would be tangent. Actually, U would be dx.
Well, u can't be dx. You mean u is 1?
Yeah. Actually, I don't know.
Okay, think about it.
I was more confident before.
Yeah?
I don't know, but is it secant squared x? No, no.
No, the derivative of tangent is secant squared. I want the antiderivative of tangent. Yeah?
1 over 1 plus x squared.
That's
Tan inverse.
no.
Inverse, you're right.
That's the derivative of tan inverse. Yeah.
Can you put sine x over cosine x?
Seems like a nice first step. And then what would you do?
And then, I don't know mathematically why, but if the derivative of the bottom is on the top, then it turns into an ln. We're off by a constant.
Well, think about why. Let's say you're faced with doing that. How do you actually do that?
What?
Yeah.
Use substitution.
What would you substitute?
Use cosine. Then d would be negative sine.
That's where we are. And so this would mean that we have minus the integral of 1 over u du, and that's where the ln comes from. So this is minus ln absolute value u plus c, and then here your u is cosine. So that is the integral of tangent. It's minus ln of cosine. BTW, depending on where you're reading, you might see the answer in a different form. It's equivalent. This is equivalent to, if you remember how your log rules work, if you have minus ln of cosine x plus c, you can actually take the negative 1, move it up, and you get 1 over cosine, which is secant. So from now on you can have that memorized. So you should memorize that the integral of tangent is minus ln of cosine, or the integral of tangent x is ln absolute value of secant. So you'd figure that out with substitution. But of course, tangent is one of the big three trig functions. So you should probably know what that antiderivative is by heart. Secant is a little more challenging. How do you integrate secant of x? And I'll be the first to say the most common method isn't intuitive at all. It's not really something you can figure out. The ones that you can figure out kind of brute force, they are very ugly and probably just not worth your time as a Calc 2 student. But the standard trick here is to multiply and divide by something that at first seems like a very odd thing to multiply and divide by. We're going to multiply by secant x plus tangent x and divide by secant x plus tangent x. Okay, just bear with me a little bit. What we're going to have at this point is secant squared x plus secant x tangent x all over secant x plus tangent x. Now does anyone see what we can do? Anything jumping out at you at this point? Yeah?
I don't want to say it. It's like, can you use like a, it was using like a right triangle, and but that's a trick. So
Do you, yeah?
Well, I mean, the derivative of secant is secant exponent, so that's it.
Yeah? Well, that's a part of it. What about the other part? What about the secant squared? What's the connection there? It happens to be the derivative of tangent, right? So, ideas? Yeah?
You make u secant x plus tan x.
Substitution. U equals secant x plus tangent x. And you're going to realize that if you take the derivative of that, derivative of secant is secant tangent. Derivative of tangent is secant squared, which happens to be the numerator now. So this all just boils down to 1 over u. Which of course is going to be equal to ln of the absolute value of u plus c. And our u was this, so it's ln of secant x plus tangent x plus c. That's the integral of secant. Something else worth memorizing. Here's another question. What about if I ask you to integrate tangent squared x dx? Huh? Think about it. Ideas?
Do you make it sine squared x over cosine squared x? Maybe use like a trig identity or something to make it, you know, like cosine squared x equals 1 minus sine squared x, or that just not work.
Okay. So what identity would you apply?
I don't know.
No, just
I guess like,
guess. Yeah.
so it's, I guess substitute out cosine squared x for 1 minus sine squared x.
Okay, you could do that. Here's one idea though. You probably don't want to make the denominator more complicated, right? So if you have a fraction, it's always better to do a complicated numerator than it is a complicated denominator.
Yeah.
Not that it's never going to work, but it's probably not the first thing I'd try.
Okay.
So if I'm going to do some sort of trig identity substitution here, I'd probably change the numerator to that. And after, okay, what can you do now?
Try to use substitution. You can
What would you substitute?
cosine squared x for u, or
And the du would be what?
the sine squared x 2x, or that would be
If u equals cosine squared x, what is du?
Negative sin, or negative 2 sin x cosine.
Right, you need the chain rule there. You have to think of this as cosine all squared, differentiate the outer function, multiply the derivative of the inner function. You get minus 2 cosine x sine x, which doesn't seem to help. Anything else? I mean, when you see it, you're probably gonna go,
Could you just rewrite it
as?
as 1 over cosine squared x minus cosine squared x over cosine squared x. So
Okay.
that minus 1, yeah.
And what's this?
secant squared.
But isn't that an identity to begin with? Like, you could have done that from the very beginning. Right? Tangent squared is secant squared minus 1. So remember, we have the Pythagorean identities, cosine squared x plus sine squared x equals 1. Now, one thing you could do is if you divide by, there are two other identities that are very closely linked to this. If you divide by cosine squared x, what's going to happen is they're going to have 1 plus tangent squared x equals secant squared x. Or in other words, you can solve for tangent to get secant squared minus 1, which that's a step you could have made from the very beginning. Another one that often comes up is that if you divide by sine squared, you would get cotangent squared x plus 1 equals cosecant squared x. So that's another identity that follows closely. But you literally just derive that identity by some more complicated way. But hey, you live and you learn, you feel your way out, you start to learn, and I'll probably give you guys some ideas when we learn another, maybe after the end of this section I'll start to tell you guys certain priorities, certain things you're going to look for first versus second versus third when approaching this random integral that you kind of don't know what to do. There are certain guesses that have a higher chance of working out for you than something else. But once we have another couple techniques under our belt, we'll worry about starting to populate that list. So you can actually just jump from this to that. Can we do that? What's the integral of secant squared?
Tangent.
Tangent. Because we know that the derivative of tangent is secant squared, and the formula of theorem of calculus tells us that. Okay. 1 is x. So that's that. All right, let's get into the meat and potatoes of the section, right? So these two things, being able to integrate secant and tangent, that's going to be useful. But just in general, having awareness of how your trig identities can come into play is useful. But now let's go to the main event. events. Okay, so we are going to, the first event is we learn to integrate the form. Sometimes sines and cosines come together in a product, and I want to be able to integrate such a thing. Now, there are certain cases that we can actually look at. So there are some cases here. So one, here's a possible scenario. We can have both n and m are odd integers. We can have n is odd, n is even. We can have n is even, m is odd, or we can have both are even. Now cases 2 and 3 are very similar, but cases 1 and 4, they are different. We're going to learn to deal with them. So here we're assuming that n, m are positive, or at least non-negative integers. Alright, so you might need to be able to integrate like a sine cubed times a cosine squared, or a sine times a cosine, or a cosine to the 5th times a sine to the 9th, or something like that. And we can deal with them in cases. So let's take them one at a time. Case 1. N and m are odd. Okay, so there's a general strategy for this case. You are going to, so here's the strategy. You're going to save either a factor of either a sine x or cosine x. Now there is a rule that you might want to follow, and you probably want to save the one with the lowest power to begin with. At least that's the recommendation. It'll work even if you don't do that, but your life is going to be a lot easier in general by doing that. So you're going to kind of isolate one of the factors of either sine or cosine. Then you're going to use an identity to help you if necessary. Change any remaining use the identity cosine squared x plus sine squared x equals 1 to change everyone else to the other trig function as necessary. Finish by substitution. U equals the other trig function. So let's do some examples here so you can see what I'm talking about. I only have one example for this case, but we're going to be sick of examples by the end of this section. Sine cubed x times cosine to the 7th x. Let's say you wanted to find that integral. Now, we're going to save a factor of one of the trig functions. It is recommended that you save the one that starts with the lowest power. I'll probably do a version where we save the one with the highest power so you can kind of compare and see what would have happened. So, here sine and cosine have odd powers. Sine has the smallest odd power. So what I'm going to do is I'm going to leave a sine alone. I'm going to split it up and separate it. So now that sign, the purpose of that sign is to act as my du. I'm going to use this guy to change everyone else to the other trig function, the one I didn't save, which means I want everyone else to be a cosine because I saved a sign. Save sign, change everyone else to cosine. So we change everyone else to the other trig function, and we're going to use this identity to do it. So I can think of sine squared by applying that identity. It's 1 minus cosine squared. And then you can finish up with a substitution. U equals the other trig function, which in this case is cosine. Your du is going to be the sine x dx. So this part is your du, and so that leads to the integral 1 minus u squared times u to the 7th dx. And that one we should know how to do. Let's just crunch it out. You can now just distribute and use the power rule. So this is u to the 8th over 8 minus u to the 10th over 10 plus c. Now we back substitute. That was a cosine. So that's cosine to the 8x over 8 minus cosine to the 10x over 10 plus c. And that's how you do it. Any questions on that? Yeah.
Like if sine of x was originally like to the 5th power, and we still took out sine x,
Yeah.
when you replace it with 1 minus cosine squared x, what would it look like? Like, do you put
So if you had
exponent?
sine to the 5th, cosine to the 7th,
Right.
I'd still save a sine. Here I have sine to the 4th. And the trick is I would think of this as sine squared squared. And so then I would have the sine x times 1 minus cosine squared squared times cosine to the 7th. And then do the same use of u squared will go here, u to the 7th goes here. Ultimately you have to multiply out. And that should give you some appreciation for why you want to save the guy with the lowest power. Well, let's look at what happens if I save the guy with the highest power. Alternatively, suppose we saved the cosine the highest power. Now, you'd still eventually get to an answer, don't get me wrong, but you're going to like it a lot less. So here I would have a sine cubed x. Here I'd have a cosine to the 6x times a cosine, right? So I save a factor of the cosine. Now what's going to happen is this, I'm going to think of it as cosine squared cubed. And so that's going to be sine cubed x. This is going to be the cosine x dx. And at this point, I can go, okay, so this is going to be sine cubed x. This is going to be 1 minus sine squared x cubed. And now I have to worry about expanding a cube, right? So I'm going to have a bigger expansion happening if I save the factor from the bigger guy, right? So while it would still work out, I mean, technically we do know how to expand this. It quickly gets annoying, right? So the fourth power, you're gonna have to remember the Pascal's triangle and all that stuff. It'll get annoying pretty quick. So to save yourself some of the pain, just save a factor of the lowest guy. Even though you can, this would still work ultimately. Yes?
Isn't the derivative of cosines negative sign?
It is negative sign. He's paying attention. Where the rest of you sleeping? About that time, it's bedtime. Yeah. Having a math class way in the evenings is kind of weird. It's better than having it at 8 a.m. though. I don't know why we do that. Okay, so let's deal with another case. I forgot what I wrote for case 2. Sometimes I don't even follow my notes in order. Case 2 was
N is odd,
n is even. Here, you can kind of guess what the strategy is going to be here, because if something is odd, it means you can save a factor, and then the thing that's left over will be even. Then you can use this guy. So the idea here is, and I had the sine to the n. This is sine to the n, cosine to the n dx. So if the n is odd, you're definitely going to choose to save a factor of the sine. Change all remaining sines to cosines using cosine squared plus sine squared equals 1. Then you're going to do a substitution. U equals cosine. Do some examples here. Let's look at sine cubed. Let's integrate that. And let's look at sine cubed cosine squared. So you can notice that in this situation here, there's no cosine. You can think of it as meaning the power m is 0. So you just get cosine to the 0, which is 1. And so 0 is an even number. So that's covered by that case. Now another calculation. So we have sine cubed. Here the power of sine is odd and the power of cosine is even, namely the power of cosine is 0. What we're going to do then is we're going to save a factor of the sine. I can then change this using the trig identity to 1 minus cosine. I can then do a u substitution. U equals cosine du is minus sine x dx. And so this will give us the integral u squared minus 1 du. Cosine cubed x over 3 minus cosine x plus c. That's how we integrate that one. Do that one quickly. Tell me the answer when you're done. Okay, what's the answer? Yeah?
Is it negative cosine x to the third divided by 3? Plus 2 cosine x to the third divided by 3 plus cosine to the fifth divided by 5 plus c.
These are both to the third?
Yes. Yeah.
Oh, so why didn't you just combine them?
Oh.
Or did that end up? Okay, let's actually see where that came from. So there's an odd power of sine, so I'm going to save that. Let's put them to the back just for aesthetic reasons. I'm going to change this guy to 1 minus cosine squared x. And then I just do a u equals cosine x, where du is going to be minus sine x. And so this, we're going to get a minus 1 minus u squared times u squared du. Multiply this out, this is u squared minus u to the fourth du. And so this is going to be minus u cubed over 3 plus u to the fifth over 5 plus c. would just have that one. I'm not sure where this came from. Similar strategy here. I would save a factor of the cosine. Change everyone else to sines. So this I would think of as 1 minus sine squared, all squared. And so now I can do a D substitution. It'll make the writing a little bit easier. U equals sine of x. Your du is equal to cosine of x dx. So this just becomes 1 minus u squared squared u squared du. So expand this, 1 minus 2u plus u to the fourth, 1 minus 2u squared plus u to the fourth times u squared. Then you're going to have u squared minus 2u to the fourth plus u to the sixth. Then you're going to have u cubed over 3 minus 2u to the fifth over 5 plus u to the seventh over 7 plus c. So sine cubed x over 3 minus 2 sine to the fifth x over 5 plus sine to the seventh x over 7 plus c. You can integrate that guy. Now this one isn't strictly obeying the form, but thought I threw out a little challenge problem there. What would you try for this one? Like this? Yeah?
Could you take out a cosine x to the top? Leave it like cosine x times cosine squared x. And then, so, I guess your u would be sine x, but
Okay. Well, if you set u equals sine x, what's going to happen? Your du would be? Huh? So the cosine x dx?
yeah,
Which is, it's that part here.
yeah.
So this is going to be a u, that's going to be the du. So you now have to figure out what to do with this guy.
Right. Then you can use the identity.
Mm-hmm.
So that'll be 1 minus sine squared x. And then you could make that 1 minus u squared.
So that all ends up, after the substitution, this will all end up being u was sine of x, so that's 1 minus u squared that whole thing goes away because that's the du, and then I have radical here in the denominator. Okay, how do I integrate that? Just divide and do the power rule. So this would be u to the minus 1/2, and that would be 4/2 minus 1/2. Add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. So now we would have u was sine of x, so this is 2 radical sine x minus 2/5 sine x to the 5/2. So the principles you pick up here can work in other forms. Again, it's just something that you get used to. We'll stop there. We'll deal with the last case tomorrow and then actually jump into trig sub. It'll be a lot of fun. Trig sub is it's going to be annoying. But then I'll tell you when to try to avoid trig sub, if at all possible.